loud. For the purposes of the recording, I'm sorry that I came in part way. Okay, so if you ever looked at your code, have you? I'm asking you the question. Have you ever looked at the code and say, holy shit, this was never going to work? Okay, that's an example. If you see that, an obvious error, okay, then that's an exception to maxim number one. Okay? Now, the problem with not obeying maxim number one is you're chasing a moving target. Let me tell you about Mickey Cohen. Maxwell Cohen was the founder. When I went to high school, I was the first class into this beautiful new high school. It was a high school dedicated to marine biology. Maxwell Cohen was the founding department chair of science. And I call this the Mickey Cohen's law in honor of him. He passed away this year. And that is, where there's one, there's many. Okay? A crash or a bug is typically a series of unfortunate events. Where there's one, there's likely more than one. Now, take a look at this meme I made. Say, that's a crash. If you're looking for the bug, you have to go backwards on the track, right? And so somewhere 100 yards back, 500 yards back, a mile back, I don't know, the wheels started to come off the tracks. It's a while later that the locomotive is a smoking heap in the ground. Okay? So remember, software artifacts, which is what the science community calls a bug, software artifacts are a series of unfortunate events. Where there's one, there's many. Okay. All right, maxim number two. I've said previously that bugs are typically very talkative and that it's your job to take in, drink in what the bugs are trying to tell you. They want to be found. Bugs want to be found. And if only you take the time to take in what they're trying to tell you. Okay? There's Mr. Bug. Anybody recognize the South Park episode where people were looking for the internet? Okay, let's move on. Okay, I call this Conan Doyle's law. When you've eliminated the impossible, whatever remains, however improbable, must be the truth. That was written in The Sign of Four. Actually, I understand now it appears in a number of Sherlock Holmes stories, but I know for sure in The Sign of Four, written in 1890, Arthur Conan Doyle wrote that line. When you have eliminated the impossible, whatever remains, however improbable, must be the truth. Okay, I'll hit you right over the head with this. Have you ever said, the bug can't be here? There you go. You are making an assumption that the bug can't be there, right? So when you've eliminated the impossible, whatever remains, namely that section of code, the bug can't be there. However improbable, must be the truth. So I'm going to ask you to make it your habit to always question your assumptions. Debugging, as you debug, you typically make loads of assumptions. When you find yourself hitting your head against the wall, start questioning your assumptions, because they are the improbable things that remain. Okay? Write in small units, test in small units. Write in small units, test in small units. Or a different way of saying it, write a little, test a little, write a little, test a little, write a little, test a little. Every line of code you write needs to be vetted so that you're always building on a firm foundation. Never go to step 2 before you're sure step 1 works. Unit tests are a great idea here. You might actually write a little bit of extra code to do the test, and then perhaps comment the test out. Maybe. The point is, write a little, test a little. Okay? Another of my rules, always play defense. There are techniques known as defensive coding. I will give some examples, but always play defense when you're coding, because the extra work involved in writing defensive code is finite. Debugging time is not finite. I don't know when it's going to end. Okay? Okay, that's it. Those were the rules. Just those 4 rules. Basically, understand debugging as a science and use the scientific method as it applies to debugging, and then 4 maxims, 1 corollary. Okay, and now we're going to get to the dialogues. Do you have any questions at this point? Okay, now all of these conversations actually happened. I just shortened them to make them fit here. This whole talk, the whole talk, was inspired by Kung Fu Panda. Okay? Especially when the little guy, Dustin Hoffman, I think, Master Shifu is his name, is that right? At some point he says, lean closer. And the panda does, and he just smacks him in the head. Okay? So I've had the desire many times to say, lean closer, so I can go pop on your forehead. Okay? All right. So a student says, my code crashed. I added a printout and now it doesn't crash. It's fixed, right? No. Do you understand why a printout would fix your bug? Of course not. What you just witnessed was an example of a Heisenbug, named after Werner Heisenberg. If you look for the bug, it's gone. If you don't look for the bug, it's back. That kind of bug boils down to a pointer problem almost always, where you are, when the printout's not there, you're looking at a place in memory which just happens to have a value that doesn't cause a crash. When you add the printf or the cout, you've moved things in memory, and maybe, I said it backwards. When you add the printf, you land on a memory location with a bad pointer that happens not to crash. When you remove the printf, things move a little bit again, and now you're landing on a place that has a value that does cause a crash. Okay? So maxim number 2, I have this error. What did the error say? I don't know. I didn't read it. I just clicked OK. This was famous with Visual Studio, right? Because it would say what you have a crash, and then it says debug or continue, and when you do that, the error goes away. So you typically just click the button, one of the buttons, and it goes away. What was the error? I don't know. I didn't read it. So lean closer. Okay. Bugs want to be found. You must take every opportunity to listen, to look. Okay. Otherwise, you're just wasting time. Okay. Here's a pet peeve of mine, which everyone in this class knows. Everyone who's ever taken a class with me. My code crashes. You get compiler warnings. They're just warnings. Folks, warnings literally have the word warning in them. What better clue do you need to pay attention to them? Warning, danger, Will Robinson, danger. Okay. So when you get a warning, you fix it. Not when the project is done and you get rid of all the warnings all at once. You have 300 warnings. You get rid of them one at a time. Okay. No, when you get the warning is the moment you fix it. And especially using C++, C++ is famous for giving 3,000 or 4,000 warnings based upon one character. So always go to the first warning. Fix the first warning, and chances are good many others will disappear. Okay? Bugs want to be found. Take time to listen to them. It crashes after running for a while. Do you have a memory link? No, thanks. I just thought I already went. Okay. This actually happened. You understand what a memory leak is, where there is an allocations, the number of allocations don't match the number of frees. Okay, think about it if you were a submariner. The number of dives should equal the number of surfaces. If it doesn't, you've got a problem. Okay? Now, there's a lot of leak detection tools available to you. For example, leaks on the Macintosh, which is why I introduced it to you, and the Valgrind on Linux. But if you're using the formal IDEs like Visual Studio, a leak detector is built right in. If you're using Xcode, a leak detector is built right in. Okay? Now, here's how I used to get students on this point. When I was teaching graphics, particularly at UW, I would grade by interrogation. Okay? I have not taken a single look at your code until the moment you sit down for a half an hour interview with me. And I have you start your project running immediately. Right? It's graphics, it starts animating, what have you. Maybe it's a game, it starts doing its traction loop, who knows? And for the first 15 minutes, I read your code on paper and ask you questions about it. And only at the 15-minute mark do I look at the screen. And if you have a leak, chances are good by the time I look at the screen, you've crashed. Okay, so if you have an application that's supposed to run for an hour typically, then you better watch it and test it for 8 hours. If you have a piece of code that's supposed to run forever, like on a spacecraft or a medical device, well, at some point you're going to leave it running and check in on it. Just leave it running. And by the way, let's introduce the idea of regression testing. When you make a change to version 10, you may be breaking code from version 2. Regression testing is how one finds those bugs, right? So this is why unit testing is so important. If you write unit tests in your large application, your enterprise application, and you're ready to come out with a new version, you can run it against all the unit tests ever written. And if any of them now begin to fail, you caught it before you did any damage. Okay? After a while, my program stops responding. Do you have any infinite loops? No, I use whiles. Come closer. Pop. Okay? These are by the way, these are like the faces I would make. And, it's too bad we're not allowed to pop, because sometimes you really benefit from that. Okay. And I'm talking about pop, not a something that's going to hurt, just like you do to yourself, maybe. All right. So your program's not responding. Check a CPU utilization. Every computer system has one. It's built into a lot of IDEs. Otherwise, use the one that Windows provides. Use the one that Linux provides. Use the one that Mac provides, et cetera, et cetera. If you see a CPU go from 0 to 100% and it stays there, chances are good you have an infinite loop. Now, if you're running in a debugger, or you're running debugging code and you've arranged for core dumps to be made, you can kill that process that's in an infinite loop. If you're already in the debugger, or let me explain if you're not in the debugger, if you've arranged to have your killed program make a core dump, then you can give the core dump to GDB or LLDB. So if you're in the debugger and you kill it in the middle of an infinite loop, you do a backtrace, right? And you're going to kill it inside the loop. So if you backtrace until you find your code, maybe it was in, I don't know, some system call. If you backtrace it to your code, now you know where you are in your code, where the infinite loop is, right? Because the code you're looking at that you killed it on is inside the infinite loop, right? My code works great, except when I enter this value. Did you try single stepping with that value? If you don't leverage all the tools that your IDE gives you or your debugger gives you, then you're just giving away your time. You're taking moments of your life and just feeding it to death, okay? Make use of all the tools. Learn your environment. Make use of the tools you have, okay? Now, debuggers have, in addition to breakpoints, they also have conditional breakpoints. So suppose they also have watches. So suppose you identify a particular variable that has a value it shouldn't have. It began, you looked at it, it was right, then all of a sudden it was wrong. Okay, well, you can use the watch breakpoints, and your program will halt, pause, when that variable changes. If the value ever becomes 7, it's a bug. Okay, watch it, run your code, the debugger will watch until that variable becomes 7. That's wonderful. However, that kind of breakpoint really slows down your code, right? Because every instruction that your program executes, the debugger has to pause it and look to see if the conditions of the breakpoint have been satisfied. I looked everywhere for my bug. Did you look here? It can't possibly be there. Okay, we talked about this one. And once again, your clue that your assumptions are wrong is when you get to the point where you say, I've looked everywhere and I can't find this bug. Well, guaranteed you haven't looked everywhere because you've isolated some code that you know to be perfect. Chances are good that's where the bug is, in the perfect code. Okay? So defensive programming and Doyle's law. Okay, I looked everywhere. Did you look here? No, I can't possibly be there. That's the same setup as the previous slide. But let's talk about something else. Have you been introduced to assertions? Raise your hand if you know what asserts are. Okay. So assertion is a powerful debugging tool. When you put an assert into your code, you are asserting a Boolean condition. In other words, you are standing on the mountaintop and declaring, I know the following to be true. And the assert will trigger if what you know to be true isn't actually true at some point in the execution of the code. It will halt you right on that line of code. One thing to remember is there's 2 ways to build your code. One is with debugging instrumentation, and the other is not. When a product is released, it is typically released without debugging information. Because debugging information, the debugging instrumentation, causes the resulting code to be a little slower, sometimes a lot slower. So when a company is ready to release their software, they remove all the instrumentation so that the code can be optimized and run as fast as it can. So you can leave asserts in. You don't have to comment them out because the preprocessor will remove them if debugging information is not supposed to be there. So if you're optimizing your code, the asserts disappear. Okay? All right, so here you see it. An assert is, you can get to include assert.h, or you can include cassert in C++. And that's all there is to it. It's assert, I claim the following is true. And then in the parentheses, you put that Boolean condition. So for example, assert I equals 7. I equals 7. You're saying, here's my red line. My red line is I know this value is 7. If it's ever 6, your program stops right there and tells you why. Okay. My program worked yesterday and I wrote 5,000 lines last night and now it doesn't work anymore. Professor, please tell me why it doesn't work. Okay, here's Tweak from South Park. Tweak is named Tweak because Tweak, as you see, loves coffee. All right, so you were up 5,000 last night and you wrote 5,000 lines. Maybe you did some coffee. Maybe you did something else. Who knows? But you were on a roll. You were in the zone. The sometimes it feels like coding is food poisoning. The code just vomits out of your fingers, right? Okay, beware. Never forget. Write a little, test a little. Write a little, test a little. Okay, you're finding a bug, right? So you're trying to find a bug in a haystack. Do you want a small haystack or a big haystack? You wrote and I've done this. I myself have done this. I've written 5,000 lines of code, 10,000 lines of code overnight. And it really did feel like food poisoning. The code had to come out. But without testing, write a little, test a little. If you have a bug, good luck finding it. Good luck. Okay. Here's an example of defensive programming. Well, here's not an example of defensive programming. I tell people to write comments. True? True. Okay. I commented like you told me. I++ semicolon. I incremented I. Okay. Lean closer. Pop. Okay. Comment what you're thinking about, not your code. Comment the story of your code. Comment your thinking, right? Because when you come back to this looking for a problem, when you look at I++, you instinctively know that you're incrementing I. But maybe it's not clear why you're incrementing I. Maybe it's not clear. Maybe it's not obvious. When you come back to your code, you have to get back in the zone. You have to get your head back inside the code. And writing, describing, and documenting your thinking, which happens inside your head, helps you to get back inside your head. Okay? Comment your thinking, not your code. Okay? Think of the next person to read your code. They have to get into your head, including you. You have to get back into your own head. Now, here's an interesting one. I recommend you write the comments before you write the code. And that's a defensive programming technique. So what I mean is, you're going to write the story of your code. You are going to write the higher level functioning of the algorithm. You'll be describing how the algorithm and the data structures interact. Remember that a program is an interaction between algorithms and data structures. They come together to create your application. Okay? So if you do what I'm saying here, if you write the comments before you write the code, you'll be hearing yourself think. You'll be hearing yourself tell the story of your code, and you might just find that your code would never have worked. So sometimes that happens. Why would you spend hours writing the code and then even more hours debugging the code only to realize the code would never have worked? You made a bad assumption. You designed a bad data structure. Has it ever happened to any of you where you got to a point where you say, you know what, I have to start over? Okay. So write the comments before you write the code. It's like a one-person code review. Oh, I love this one. My code doesn't work. Professor, help, please. Teacher says, what does I need sleep do? And the student answered, I don't remember. I was tired. This one is a literal word for word. Okay. Descriptive variables can be really, really helpful. Sometimes they get long, but you know what? Keystrokes are finite. Debugging time isn't finite. And your IDE is probably going to allow you to hit the tab key and fill in the rest. Okay? Don't use I unless it's something absolutely trivial. Don't use I need sleep. Don't use WTF, unless it stands for watch timer function. I don't know. And in which case, it should have been named watch timer function. Okay? All right. Now, the languages we use, assembly language, no, but many other higher level languages allow you to do multiple statements on one line. An example of defensive programming says, don't ever do that. Why? Because your mind, as a human being, you will naturally, when you're searching for the bug, you'll pay more attention to the first one and the last one, and you'll pay less attention to the ones in the middle. That's what humans do. So resist the temptation to do this. Don't do that. New lines are free. Okay, use them. All right. What's over there is actually valid syntax. If you had the right typed variables in there and values, that would pass a compilation. So you think you're so cool. Coding is not a contest, right? To outdo the other person. Look at it. I'm doing 12 things on this one line. Wow, and you took 12 lines. Ha, loser. You got a bug in there. And how easy is it to find versus breaking these things out? The optimizer is going to come along and put it together in the optimal way anyway. Okay, so chances are the student who has this code and the student who has the code broken out into separate lines and optimizes it, they're going to generate the same code. But this one is impossible to debug. Okay, for one thing, can you see my mouse? Anybody? Okay, for one thing, it's got side effects. Okay, this is a side effect. Don't do that. Another thing is, well, here's another example of a side effect. Okay. This is syntax which you'll almost never ever see. Does anybody, where'd my thing? Does anybody know what this means? Comma. Right. Yeah. So see that? Don't do that. That's not a function call, folks, but that is valid. What it means is take the first part, do it. Take the second part, do it, and throw the results away. Okay? So don't do that, because chances are you'll never master it. Okay? All right. So side effects, just avoid them. You're not being cool. Frankly, everybody who's on your team will just think you're an asshole. Okay? All right. The bug can't be here. I pasted the code from Stack Overflow. Really? That code is different from this code. Oh, well, yeah, I fixed the bug. Well, I got a few things to say here. One, when you paste code without perfectly reviewing it, deeply reviewing it, you're just copying their bugs. They're now your bugs. If you don't understand the code, it's like when I said you have to understand the fix. If you don't understand the code, it's just as bad. Their bugs are now your bugs. And then what happens if you take somebody's perfect code and you believe that it's not quite perfect, so you make a little change? All right, now you've introduced a new bug. Okay. Now, this is describing something else. Down at the bottom, code abstraction is actually a defensive technique. Okay. Code and follow. Okay. I've given you a little mantra. Write a little, test a little. Here's my second mantra. Code in one place, test it in one place, fix it in one place. Have you ever, be honest, have you ever swept out a section of your own code, copied it, and pasted it someplace else? Maybe you had the thought, I'll come back to this someday and make a function out of it. No, and you never do. But no, make a function out of it now. If you copy code and paste it, that is your sign that it needs to be a function. Why? Code in one place, test it in one place, fix it in one place. I can't tell you how many students went down in flames because they pasted a set of code in 11 places, discovered it had a bug in that code, and fixed it in 10. Okay? When you don't get every single one fixed, you still have that bug. Code in one place, test in one place, fix in one place. Don't copy paste code multiple times. Figure out how to make it a function. Make use of parameters to customize the invocation. Maybe there's just subtle differences in the use of the code. Still, make it a function. Okay, here's defensive programming. Again, and Doyle's law. Again, the variable foo has to be one of these values. We're looking at a switch statement, right? And if it isn't one of those values, that's not possible. There's Doyle's law, right? Because, oh, that's not possible. When you've eliminated the impossible, whatever remains, ... Okay? And also, here's the thing. Always code the default case and always code the impossible else. Okay? Now, in one of the greatest movies ever made, Princess Bride, this person is just drank poison because he's been faked out by the hero. And he says, inconceivable. That's his catch line. Inconceivable. Impossible. And yeah, he did drink the potion, the poison. Okay. All right. So always code the default case. Always code the impossible else. So if you have if blah, 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 all right, then maybe you should put in if blah, blah, blah. If you have an if, else, if, and you leave out the last else, maybe you should put it in there because if only it said, got here, I wasn't supposed to. Let me tell you a story told to me by a former colleague at UW-Madison. So Ben Liblet went to work before he became a professor, and he worked at a company that makes the one of the big time communication chip companies. If you're thinking Qualcomm, you would be correct. And there was a code review, and they're looking at some code. And inside there's a loop, there's an inner loop. Maybe there's a absolutely time critical loop that's executed 1 billion times. It has to go as fast as possible. But Jennifer noticed a situation in which there's an assumption. And in the code review, she suggested putting in the impossible else, right? Or putting in a tiny test to test the assumption. And Boris, with hairy arms, screams at her, no, this is too time sensitive. We have no time to waste on an unnecessary test. So the product ships, and it's out in the market. Millions of people are using it. And one day, tech support, frontline tech support, forwards to the engineers a peculiar error message. They had no idea what it meant, so they upped it, they escalated it from frontline support to the engineers. And the error message said the following: tell Boris Jennifer was right. Okay, so before the code actually shipped, she slipped in the test of the assumption. The product worked. It worked for 6 months. Nobody noticed the little time delay, but the test was there, and one day it tripped. And it would never have been found otherwise. Okay. My code doesn't work. Professor, please. You're not checking return values. What? That function has a return value? Return values are meant to be checked. Okay? It's not a hard concept. All right? If something has a return value, a documented return value, you should check it. People might say, oh, but it makes my code ugly. Well, I'll get to that. But let me look here. This was thanks to my best friend, Professor Bart Miller, who is a world famous researcher in security. And take a look. SU is a program on Linux that allows you to become someone else temporarily. In the Linuxes we've been using, SU might not be there. It could be sudo, sudo, sudo. Okay, terrible joke. Two roommates, they're both lounging, watching TV. One says to the other, make me a sandwich. And the roommate says, make it yourself. And then the first roommate says, sudo, make me a sandwich. And the other roommate goes and makes the sandwich. Okay, so this is an example. SU also stands for, you could think of it as substitute user, but it's also super user, because this is how an ordinary user becomes root, the master user. Okay. Now it runs, SU program runs set UID to root. So when you do an ls minus l, you see an S here. That means that the program itself always runs with the privileges of the super user, always runs with unlimited privileges. Otherwise, how would it make you become someone else? It has to be the master of all. Okay, now suppose it was written like this. Here's the actual, whoops. Here's the actual set UID call. And then you become someone else, and then you run the program that they want you to run as someone else. Okay, now this returns a return value, but it's not being checked. So what you do is you run SU with a user that doesn't exist. A user that doesn't exist. This fails and falls back to executing this command as root. You see why you have to check return values. Now, granted, some return values are more important than others. Okay, let's take a look at, oh, here you go. There's something missing here. It's among my reserve slides that I will get to, which I will do by let me skip. Okay, I don't see that slide here anymore at all. So what I was going to talk about is you can, in some circumstances, write your code as if nothing can go wrong using exceptions. C++ or Java, et cetera, exceptions. So if you write your code without any error checking, and something does go wrong, which throws an exception, you could use the exception handler as the place to fix things up after having discovered that a return value is bad. So your code won't look ugly. Okay, why would checking error values for everything make your code look ugly? Well, it might make you nest your code 50 levels deep. That's a problem. It might make your function, instead of your beautiful 9-line function, it might make it 18 lines because they're error checking. But the bottom line is you have to check. Okay, return values are there for a reason. Okay, now what you see here, the person you see there in the background is Andy Warhol. And Andy Warhol was a force of nature, artist and celebrity. He was the coolest guy in the 1960s, the coolest guy on the planet in the 1960s, 1970s. And this is the quote: "Dying is the most embarrassing thing that can ever happen to you because someone else has to take care of all your details." All right, now what is that doing in this book, in this lecture? Never just crash. Never just crash. Okay, maybe you find a situation in which you can't possibly proceed. Then you, instead of just crashing, you should give the user some feedback, and then you can gracefully exit. Okay, now feedback. Microsoft was famous for their feedback errors. For example, error and 8 digits of zeros. Okay, the error code number was 8 digits of zeros, and the error string was error colon no error. Microsoft error messages were so bad that there's this following joke. Traffic helicopter up in Seattle, wherever Microsoft's headquarters is. Traffic helicopter, they're up in the air. This is before GPS. They get blanketed with fog. They have no idea where they are. So they descend very slowly so they don't bump into anything. They find an office building. They inch closer to the office building, and people in the office building notice this. They start looking out the window. The pilot raises a sign that says, "Where are we?" Somebody inside the office building makes a sign, holds it up. It says, "You're in a helicopter." And the pilot says, "I know exactly where we are. We're next to Microsoft." "How did you know?" the co-pilot says. "Well, because Microsoft error messages, they're correct, but they don't tell you a damn thing." Okay? Take care of your own details. And we have a little time. Let me show you some of the extra slides that are invisible. But you have the PDF, you have the PowerPoint file, you can see them. Let's see. Okay, there's this, which you can see. Okay, I crash every time I get here. That's the best crash you can possibly have. You should sing and dance for joy, because if you get there every time and every time it crashes, you know exactly where to look. Okay. All right, debugging is a process. It's part of the process. You shouldn't be frustrated by debugging. I enjoy debugging. I think debugging is the best part of programming. That doesn't mean I write bugs on purpose, but it does mean I actually enjoy debugging other people's code. I once debugged a point of sale system over the telephone written in a language I didn't know. Okay. Why can I do that? It's not magic, it's science. Now, when you don't understand the science, it looks like magic. Okay. I have told you, given you example after example of how your code can mean the difference between life and death. I won't repeat it here, but I'll just say you should code like it means life and death, life or death. Okay, so those invisible slides. Well, here's an example of one of those terrible things that can happen. Here's another example. Here's something. This is interesting. These Dijkstra and Knuth are gods, right? They inhabit Valhalla and Mount Olympus at the same time in computer science. Look them up. Okay. Now, here's what they had to say about debugging and testing. So, testing can only prove the presence of bugs, not their absence. Think about that. To say, you can never really say there are no bugs in your work, because that's like trying to prove a negative. So testing is critical importance to gain high confidence, but never be arrogant. Never say it can't be my code. It's Austin's code. You know, always be humble with respect to correctness. And this is a great one. Beware of bugs in the above code. I've only proved it theoretically correct, not tried it. Okay, so especially beware of fixing a bug or writing code and not testing it. And another hidden slide. I wrote my own blah, blah, blah. Why didn't you use the one from the framework? Because I wanted to write my own. Okay. To become a framework, thousands of programmers have looked at the code and used the code. They probably did a pretty good job. Don't waste your time re-implementing what you can get from a framework. However, with that said, their bugs become your bugs. So by framework, I mean something like the STL, like angle in C++, angle bracket vector, angle bracket. Okay. That code, you can be sure as you can be, that it's going to work properly. There's still minute chance of having a bug, right? So don't reinvent the wheel. Let's see, another. Sometimes you should, my code doesn't work. Did you try the following? I don't remember if I tried it or not. Sometimes it's a good idea to add comments describing your previous hypotheses and what you did to test it. You don't actually have to remember the code, because that'll get really messy and ugly. But if you jot down a note of what you thought the problem was and it turned out not to be, this way in the future, you won't try it again, and someone else looking at your code won't try it either. All right, what is this one? Okay, yeah, I told you that already. Okay, the time is 3:34. I can now open the floor to questions. Let me point something out. When you make a PowerPoint or any other type of slide deck, always put in slide numbers so that somebody in the audience who has a question can say, I have a question on slide 43, rather than, you said something about beeswax being important in the production of aluminum somewhere in your talk. No, back. Anyway, put slide numbers on your slides. Questions? Do we have any seniors in this class? Okay. Now, I'm probably going to I'm probably going to watch your presentations in May. And I will mark you down if you don't have slide numbers. Okay? Okay. Questions? Arthur, please go ahead.
I think the one question that I have is about the return values. The slide where it talks about return values. And I was wondering, I don't know if this might devolve into a dumb question, but do all functions in assembly language have to end in a return value?
No, an assembly language function that is standing in for a void function doesn't need a return value. It just needs a return, but it doesn't have to have any value in a particular register. And in fact, folks, that's why void was invented, right? Because void was not initially part of the C programming language. And I think I told this story already in this class. Maybe I did. But Steve Bourne, who wrote the shell, went to Dennis Ritchie and said, hey, I can say most of our functions are void functions, but they are still returning. Let me rephrase that. Most of our functions don't return anything of value, but they have to be int functions, right? So they have to return 0. But we're not using the 0. If we add the word void to the C programming language, we can save one instruction for every function like that. And that's how void got into the programming language. Okay. Now, Steve Bourne also wrote the original SH, and he also wrote Bash that you're most comfortable with, Bash, which stands for the Born Again shell. It's not religious, it's just Steve Bourne's second shell. Okay, Arthur, does that answer your question?
Yeah, it does. I'm a bit more familiar. I'm more familiar with the return command now. I was initially confused about what
Yeah.
the could stand for.
Yeah, now think of C and C++. You could have in a void function, you can have return semicolon. But in other functions which are not void, you have to say return and a value. Any other questions?
Yeah. What do you think is the hardest kind of bugs to find or to fix?
Uh, okay, so speaking not as myself, but as an observer of others, because I find both of these straightforward to find and fix, but most other people do not. There are two kinds of bugs. One is concurrency bugs. Those are at first place. That's first place, the hardest bugs for most people to find. Because you're so accustomed to writing code that is sequential. When you start writing code that is concurrent, meaning uses multiple threads, for example, your assumptions about what's where may not hold true anymore. It runs counter to everything you've learned up to that point. So, concurrency bugs, once you hit them, they seem completely mysterious because a program might run 100 million times, run it one more time, and it crashes. Okay. The second is involving a bad pointer. Okay. And specifically, even worse subset of that is the Heisenbugs that I talked about earlier. If you move around your code at all, the bug seems to go away. Put it back the way you started, and the bug is back again. That's almost always a Heisenbug is usually a bad pointer. Now, class, how do we get bad pointers? We use a pointer after it was freed. A pointer becomes corrupted, right? Any other ways pointers become invalid? Like
Can I interrupt for just a moment?
Yeah, of course, Kyle.
How do pointers get corrupted?
Through another pointer that's corrupted already. Okay, so your program makes a mistake. So that way there's the pointer is corrupted because let's say you call a function which returns a pointer. And that function, you don't know who wrote it, you don't know them, you don't know what it does. It has a bug. So the pointer you got back is bad. All right. Then you stuff a value, you dereference it and stuff a value there. So where it was pointing was also bad. Let's say where it was pointing happens to be another pointer. Okay. Or let's say this, you overrun your stack, not the stack, your data structure, but the stack that of your function calls. If you overrun your stack, you're corrupting pointers. Okay. So corrupted pointers typically come about from other corrupted pointers. Or algorithmically, like off by one in a loop. You have an array of integers followed by a pointer in memory. You go one too far on your array of integers and you're overwriting a pointer. Got the idea?
Yeah, thank you.
Ooh. The evil mailman is coming. Bite him, bite him. Robbers. Okay. Any other questions? Okay. I will be putting out a next assignment. And it's already online. Just go look at P3 in the GitHub. And I will be at the barbecue tonight. You have a program due tonight, P2. By due tonight, which means it's absolutely due by Friday night. Okay? So I'll be there at the barbecue with bells on. That's an expression. I won't actually have bells. All right. We'll see you, everybody. Thank you for coming.
See you at the barbecue, Professor.